Okay, let's finish this lecture. Well, we want to do a further analysis of the Dijkstras algorithm. We, by working on the examples, we feel that Dijkstra's algorithm is faster than the BF algorithm. And well, how do we do a formal analysis? So let me ask you this first. So how many times is extract min called? So remember, originally we had all the four nodes in the queue, and then when we extract the mean, we take one out. And the next time we do the extract mean, we take another one out. So originally for the queue, it has all the four nodes. And eventually, our goal is we want to remove all the nodes from the queue to the S, right? So how many times do we call that? Depending on how many vertices do we have. So for each of the vertex, we have to call the extract mean once. Okay, so what is the total running time? And to continue our discussion, we have to make a few assumptions. So the number one, well, to do the extract mean, well, we are assuming that we are using a mean heap to extract to record the d values. Okay, and then well, for the adjacency matrix, adjacency list, we are using an adjacency list to record each of the edges. So remember, we have two options. We can use the adjacency matrix or the adjacency list. And usually, adjacency list performs better than the adjacency matrix. So we are assuming that one, we are using the min heap to record the d values, and another one is we are assuming that we are using the adjacency list to record the edges. Okay, so and then let's move on. So let me give you the answer first. The answer is for Dijkstra algorithm, that is the E log V. And how do we get there? Well, I'm using the same notation. I'm using the blue inks to show you the defined complexity, and then I'm using the black ink to show you the hidden complexity. And especially since we are using the min heap, there are some hidden complexities for us to massage the min heap to make sure that it works. Okay, well, the first part, well, for each of the vertex, and then we want to do the d equals the infinity. So by the definition, that is the OV, right? Because we are only visiting each of the vertex once. And remember, since we are using a min heap, we have to build the min heap with v values. All the values are infinity. However, we still have to build a min heap. So to build a min heap, that is the v log v. Okay, so the next part, uh, those are the definitions. They can all be done in constant time. Okay, and how about this part? As long as the queue is not empty, we want to extract the minimum from the queue, and then we want to add that to the S. Okay, so if you oops well, for this part, for this while loop, we know it will iterate for a total of v runs. That's right. And how about the time complexity of the extract mean? And we don't know that yet, so I'm leaving a question mark. So for this while loop here, we know it will iterate for v runs, and however, we don't know what is the time complexity for the extract mean here. So that's the reason I'm leaving a black question mark. So if you're extracting the mean value from a min heap, what is the time complexity? If we only want to see what is the mean value, that is the root, right? That is the very top of the mean heap. So to see the minimum value, that is constant time. However, we want to extract that. We want to take the minimum out from the heap. So the heap is a triangle, and we are taking the top value, which is the minimum, out from the mean heap. And then what do? We have to fix the tree, right? Sorry, fix the heap. To fix the heap, that is a log v. So the question mark is really a log v here. Okay, so the second part, that is a v multiplied by O log v. So that is a O v log v algorithm here. And the rest part, well, for each of the edge, we only visit that once because that is a directed graph, and then the total of the times, well, when we are doing this part for each of the v, we are going to try to find the adjacent nodes by using the edges. So we are going to visit all the edges guaranteed in this for loop. However, we are only visiting each of the edge once. That's a big difference, right? So for the BF algorithm, we are visiting each of the edge for the v minus 1 times. However, in the Dijkstra algorithm, we are only visiting each of the edge once. That's a big difference. So that is a OE because we are only visiting all the edges. And after that, you see, we are updating the DV values. What is the DV? Those are the values stay in the heap, right? So when we are changing the DV values, we are changing the values in the heap. And then, does that concern you? It concerned me because when we change the value in the heap, this heap may not be right anymore. So when we change the value, we also have to fix the heap again. So to fix the heap, that is a log v. Okay, so let me put everything together. So this part is the OV algorithm, and then that is the O1 part, and then we have the OV log v. And for this part, that is OE log v. Okay, we want to add those four parts together, and which is the most significant one. So it can't be this one, it can't be this one. And for v log v and the e log v, which is more significant? So remember, just now we say usually we have more edges than the vertices, right? So this means OE log v will be the more significant component. So this makes the time complexity of the Dijkstra algorithm OE log v. Okay, so that's it. That's the analysis of the Dijkstra algorithm. And well, thank you for being patient. And if you want to know more about the time complexity of the Dijkstra algorithm, and remember to read the textbook. So you don't have to read the whole chapter, but in our textbook, it is in the section 24.3, and there is just 2 paragraphs discussing about the time complexity of the Dijkstra algorithm, and this is definitely helpful for you to read this part of the textbook. Okay, so thank you, and I will see you next week.